Welcome to Lecture 9. This week we're going to start with the fundamental theorem of calculus, and then we'll move on to indefinite integrals and the substitution method, and then the substitution method for definite integrals and area between curves. First, we'll start with the most important theorem in this course, the fundamental theorem of calculus. We don't want to have to deal with Riemann sums every time we need to calculate a definite integral. We want a better way. I'm going to give you the most important theorem in calculus. If you can only memorize one theorem for the exams, then it should be this one. We need a continuous function. Suppose that f is a continuous function defined on a closed interval. And then the fundamental theorem of calculus has two parts, part 1 and part 2. We need to learn both parts of this theorem. First of all, part 1 says, then if we define a new function, let's call it capital F, with this formula. Capital F is defined to be the integral from a to x of f of t dt. Then this function is continuous and differentiable, and if we differentiate capital F, then we get the function small f that we started with. In other words, if we differentiate an integral where x is the upper limit of integration, then all we do is we get the integrand. And then part 2 of this important theorem says if f is any antiderivative of f, then the definite integral from a to b of f of x is capital F of b minus capital F of a. First, I'm going to talk about part 1, and then I'm going to talk about part 2 of the theorem. Part 1 of the theorem tells us how to differentiate an integral. If we have an integral from a to x of f of t dt, and we want to differentiate this with respect to x, we use part 1 of the fundamental theorem of calculus. So, for example, you might be given a question something like this. Find dy dx if y is the integral from a to x, t cubed plus 1 dt. All we do is we take the integrand, that's t cubed plus 1, and we replace the t by an x. The derivative of this integral is x cubed plus 1. And that's all we're doing. We're just taking the integrand and we're replacing t by x. Another one. Find dy dx if y is the integral from 1 to x of sine t dt. All we do is we take the integrand, the sine t, and we're going to replace the t by an x. The answer is sine x. Or another one. Find dy dx if y is the integral from 0 to x of sine of ln of tan of e to the power t squared dt. So we just do exactly what we did before. We're going to take our integrand and we're just going to replace t by x. The answer is sine of the natural logarithm of tan of e to the power x squared. And it's that easy. Now let's make this a little bit harder. Why is this different? This is different because x is now the lower limit. Find dy dx if y is the integral from x to 5 of 3t sine t dt. Well, we can only do what we were doing before if we had the x at the top, but we don't have that. We have the x as the lower limit. But that's not a problem because we know how to swap these around. We can swap the limits of integration if we put a minus sign in the front. And then now we have our x at the top. So now we can do the same trick. We can take our integrand, 3t sine t, and we can replace every t by x. So the answer is minus 3x sine x. Let's make this a little bit harder again. Find dy dx if y is the integral from 1 to x squared cos t dt. Okay, now we don't have an x at the top, now we have an x squared. So we're going to have to use the chain rule. We're going to want to replace the x squared by u. Then, by the chain rule, dy dx is dy du, du dx, and dy du is d du of the integral from 1 to u cos t dt. We know how to do that. And then multiplied by the derivative of x squared. We know how to do that. For the first one, all we're going to do is we're going to take our integrand cos t and we're going to replace the t by u to just get cos u. And of course, the derivative of x squared is 2x. So the answer to this question is 2x cos x squared. And that's it. That's part one of the theorem. As I said, this is the most important theorem. Make sure you learn this theorem and make sure you learn both parts of it, part one and part two. What did part two say? Part two told us how to calculate the definite integral of a function f over a closed interval from a to b. We need to do two things. We need to find an antiderivative, capital F of f. That's any antiderivative. We don't need the general antiderivative. We just need any antiderivative. And then step two, we're going to calculate f of b minus f of a. And because we're going to be doing this a lot, we need a nice notation. I'm going to be writing square bracket, capital F of x, square bracket from a to b, every time I want f of b minus f of a. So, for example, the integral from 0 to pi of cos x dx is square bracket sine x, square bracket from 0 to pi. Why? Because sine x is an antiderivative of cos x. Why? Because if we take the derivative of sine x, we get cos x. So we need to calculate sine at pi minus sine at 0. But those are both 0. We're doing 0 minus 0 or 0. Does that make sense? Does it make sense that the integral of cos between 0 and pi is equal to 0? Quick look at the graph. Yes, we have a positive piece and we have a negative piece of area. If we do positive plus negative, we get 0. Another example. The integral from minus pi over 4 to 0, sec x tan x dx. And that's going to be this area up here. And because we're underneath the x-axis, we're expecting the answer to be a negative number. What is an antiderivative of sec x tan x? An antiderivative is sec x, because if we differentiate sec x, we get sec x tan x. So we're going to be calculating sec x at 0 minus sec x at minus pi over 4. Sec of 0 is 1, and sec, or 1 divided by cos, of minus pi over 4 is root 2. So 1 minus root 2. Root 2 is about 1.4, so yes, this is a negative number. The integral from 1 to 4 of 3 over 2 square root of x minus 4 over x squared dx. We need to find an antiderivative of our integrand, and I'm saying that an antiderivative of our integrand is x to the power 3 over 2 plus 4 over x. Why? Because if we differentiate this function, we get the function that we started with. So all that's left to finish this problem is then to put in 4 and then minus and then put in 1. 4 to the power of 3 over 2 plus 4 over 4 and then minus 1 to the power of 3 over 2 plus 4 over 1. I'll leave it for you to check that that is simplifies to 4. So let's just summarize the ideas from today so far. Part 1 of the theorem of calculus tells us how to differentiate an integral. The derivative of the definite integral from a to x, f of t dt. All we do is we take our integrand f of t and we replace the t by an x to get f of x. Part 2 of the fundamental theorem of calculus says that the definite integral of f from a to b is an antiderivative of capital F at b minus capital F at a. Make sure you learn both of these ideas. Let's talk about total area next. We've seen that the integral of cos x between 0 and pi is 0. Why? Because we've got a positive area and a negative area, and positive plus negative is equal to 0. But what if we don't do it like this? What if we say that all area should be positive area? That's the idea of total area. Let me start with a different example. Think about the function f of x is x squared minus 4. I'll leave it for you to check later that the integral of f between minus 2 and 2 is minus 32 over 3. If we say that all area should be positive area, then we can say that the total area between the graph of y is equal to f of x and the x-axis between minus 2 and 2 is the absolute value of minus 32 over 3, or 32 over 3. We make all area positive. Another example, think about the function g of x is equal to 4 minus x squared. Again, I want to integrate between minus 2 and 2, and I'll leave it for you to check that the answer is 32 over 3. Total area, if we say that all area should be a positive number, we take the absolute value of 32 over 3 and we get 32 over 3. Let me show you graphs of these two functions. On the left, I have the first function, the function f. The blue region shaded in blue, that's the integral of that, is minus 32 over 3 because it's below the x-axis. But if we say that all area should be positive area, we get total area is plus 32 over 3. On the right-hand side, the second function, g, the integral is 32 over 3, and the total area is also 32 over 3. Let f of x be sine x. Calculate the definite integral of f over the closed interval from 0 to 2 pi, and the total area between the graph of y is equal to f of x and the x-axis over the same interval. I'll start by showing you the graph of this function. We want to calculate the integral between 0 and 2 pi. Well, from the graph, we can see there's a positive bit and a negative bit, so we can guess what the answer is going to be. And then we want to do total area. We want to say, what is the area if this part is positive and this part is also considered to be positive? Part 1, first of all, integral from 0 to 2 pi of sine x dx. An antiderivative of sine x is minus cos x. So we have minus cos 2 pi plus cos 0, minus 1 plus 1 is 0. We expected that from the picture. And then we're going to do total area. We want to make everything positive. So we're adding in absolute value signs. I want the absolute value of the integral from 0 to pi sine x dx, and then plus the absolute value of the integral from pi to 2 pi sine x dx. And the calculation I leave for you to check later. You can look at this later, check all the details, and check that the answer is equal to 4. So let me summarize this. If we want to find the total area between the graph of y is equal to f of x and the x-axis over a closed interval from a to b, step 1, we need to divide our interval at the points where f is equal to 0. We want to calculate the integral of f over each one of these sub-intervals. We want to take the absolute values of these numbers and then add them together. For example, find the total area between the graph of y is equal to x cubed minus x squared minus 2x and the x-axis for x between minus 1 and 2. First thing to do is to find the points where the function is equal to 0. So the first thing to do is to solve the equation 0 is equal to f of x. And if we factorize f, we get x plus 1, x minus 2. So quickly we can see that the function is equal to 0 if and only if x is 0, x is minus 1, or x is 2. So we want to split our interval at these points. Minus 1 is at the left end, 2 is at the right end. We don't need to split there. We're just going to be splitting in the middle at 0. So we take our interval from minus 1 to 2, and we're going to cut it into minus 1 to 0 and 0 to 2. We'll calculate the integral on each one of these two sub-intervals, take their absolute values, and then add them together. First one, integral between minus 1 and 0. I leave it for you to check. Please check that that's 5 over 12. And then we do the integral between 0 and 2. Again, please check that I haven't made a mistake here. Please check that this is minus 8 over 3. Take the absolute values of these numbers, add them together. Absolute value of 5 over 12 plus absolute value of minus 8 over 3, we get 37 over 12. The total area, which is shaded here in red and blue, is 37 over 12. Next, I want to talk about the average value of a function. Now, if you're following along in the textbook, this is not in section 5.4 in your textbook. I think it's in 5.3 or 5.2. So it should have been done last lesson perhaps, but it makes sense to me to do this after we talk about the fundamental theorem of calculus. The average of the numbers 1, 2, 2, 6, and 9. We know how to do this. We did this at school. Add the numbers together, 1 plus 2 plus 2 plus 6 plus 9, and then divide by 5. The average of these numbers is 4. We can also calculate the average value of a continuous function. If f is integrable between a and b, then the average value of f between a and b is given by this formula. Instead of adding numbers together, we do an integral because an integral is a limit of a sum. And then instead of dividing by how many numbers we have, because effectively we have infinitely many rectangles after we've taken the limit, we divide by the width of the interval. So it's the 1 divided by the width of our interval, 1 divided by b minus a, multiplied by the integral from a to b f of x dx. I'm going to take this formula and I'm going to put it at the top for the next few slides. Find the average value of the square root of 4 minus x squared on the closed interval from minus 2 to 2. We need to integrate this function between minus 2 and 2, and then we need to divide by the width of our interval. But there's a shortcut here because the square root of 4 minus x squared, y is equal to 4 minus x squared, that's the same as y squared plus x squared is equal to 4, or 2 squared. So we have a circle of radius 2. Actually, we have the top half of a circle of radius 2. So this integral must be a half multiplied by the area of a circle of radius 2. This integral must be equal to 2 pi. And then using the formula in the yellow box, divide by the width of the interval from minus 2 to 2, we're dividing by 4. So 2 pi divided by 4, or pi over 2. What does that look like on the picture? Now, first time people see this, they're confused a little bit because the area above the red line is much smaller than the area below the red line, but that's not relevant for us. Instead, think of it like this. Think about looking when is the function above the red line and when is the function below the red line. Roughly half the time, the function's above the red line, and roughly half the time, the function is below the red line. So it starts to make sense. Why am I saying roughly? Well, up here, the function is only above the red line a little bit, but at the endpoints, it's below the red line by a lot. So it's not going to be exactly half and half, but roughly half and half, perhaps. Another question. Find the average value of x cubed minus x on the closed interval from 0 to 1. We're going to put everything into our formula. 1 over b minus a for us is 1 over 1 minus 0, or 1 over 1. We can forget about that. Effectively, here we're just going to be doing the integral of g between 0 and 1. And I leave the details for you to check. You should be able to do this by yourself. The answer is minus a quarter. I'll show you a picture of this function and its average value. Again, intuitively, we can think the function is above the red line roughly half the time, and it's below the red line roughly half the time. Not exactly, but roughly. And then if we think like that, then it looks about right. Before I finish this section, I want to make a comment about the difference between indefinite integrals and definite integrals. Remember, if we have an indefinite integral, for example, the integral of f of x dx, that's a function. But a definite integral is a number. These two things look similar type of notation, but they're different things. I have a function and I have a number. For example, the indefinite integral of x dx is x squared over 2 plus c. Don't forget the plus c. Of course, there's points in the exams for writing plus c. And the integral of cos x dx is sin x plus c. Moving over to the right-hand side, the integral of x between 0 and 1 is a number, it's the number of half, and the integral of cos x between 0 and pi over 2 is also a number, it's the number 1. Section 5.5 is about indefinite integrals, so functions, and the substitution method. By the chain rule, we've looked at this before, the derivative of u to the power n plus 1 over n plus 1 is, well, derivative of this function with respect to u, or just un, multiplied by du dx. So if we go backwards, the integral of u to the power n du dx dx, we need an antiderivative of our integrand, but we see that above. An antiderivative is u to the power n plus 1 over n plus 1. But wait a minute. We also know that the integral of u to the power n du is also u to the power n plus 1 over n plus 1 plus c. So it looks like these green things are the same. It looks like du is equal to du dx dx. And that makes sense in terms of notation if we can imagine that the dx is cancelled out. We can't really imagine that because du dx doesn't really mean du divided by du unless we think of differentials. But we can imagine it like that. So, for example, find the integral of x cubed plus x all to the power 5 multiplied by 3x squared plus 1 dx. To solve an integral like this, we need to make a substitution. We're going to introduce a u, and for this integral, I want to let u be equal to x cubed plus x. Why? Well, I'm looking at my integrand. I have an x cubed plus x, and I have a 3x plus 1. One of these is going to be the correct choice, and one of them isn't. For this one, it's going to be x cubed plus x. If you're unsure, try both of them and see which one works. Then, using the idea from the previous slide, du is the same as du dx dx, which is 3x squared plus 1 dx. I have a 3x squared plus 1 dx. So we can do the substitution. We can change the integral we were given, the integral of x cubed plus x all to the power 5, 3x squared plus 1 dx. We can change that to the integral of u to the power 5 du. And then that's a lot easier. We've changed a difficult integral into an easy integral. Easy integral we can calculate easily. U to the power 6 over 6 plus c. Don't forget the plus c. And then finally, just as we were doing when we were using the chain rule, we can't finish with an answer with u in. We need to put x back in. So our final answer should be 1 over 6, x cubed plus x all to the power 6 plus c. You can think of the substitution method as doing the chain rule backwards. For derivatives, we had the chain rule when we were doing a derivative of a complicated thing. For integrals, we have the substitution method. And the idea is the same. We're just doing the chain rule backwards effectively. Find the integral of the square root of 2x plus 1 dx. We need to do a substitution. We need to choose some function to be u, so as we can make this easier. Looking at our integrand, there's a 2x plus 1 here, so it makes sense to choose this for u. Step 2, I want to do the du is equal to du dx step. Du is equal to du dx, which is 2 dx. Now I don't have a 2 dx up here. I only have 1 dx. So I'm going to divide both sides by 2, and I'm going to be using the formula dx is a half du. And then I'm ready to do my substitution. Square root of 2x plus 1, I can change that to square root of u, or u to the power of a half. And instead of dx, I can put in a half du. So we've taken out complicated integral, a slightly difficult integral, and we've changed it into a half integral of u to the power of a half du. We've changed this into an easier integral. And then after that, the last line you should be able to do yourself, so I'll leave that for you to check. So that's the idea. Let me give you the formal theorem. If u is equal to gx is differentiable, if g is a function from the real numbers to some interval I, and f is a function from some interval, from the same interval I to the real numbers, which is continuous, then the integral of f of g of x multiplied by g prime of x dx is equal to the integral of f of u du. So as long as everything is nice, continuous differentiable, etc., we can replace g prime x dx by du, and we can replace the g of x by u. Let's do another example. Find the integral of 5 sec squared 5t plus 1 dt. Well, first thing to do is to look at our integrand and decide which function are we going to choose for u. And I see I have a 5t plus 1 here. It makes sense to choose that for u. Step 2, I can find that du is 5 dt. Do I have a 5 dt in my integral? Yes, there's a 5 here and there's a dt here. I can replace this 5 dt by du. So our integral is equal to the integral of sec squared u du. And we've made this much easier. We know an antiderivative of sec squared. We know that that's just tan. Why? Because we remember that if we differentiate tan, we get sec squared. Finally, replace the u by 5t plus 1, and we get our final answer. Tan of 5t plus 1 plus c. Let's do another example. Find the integral of cos 7 theta plus 3 d theta. Step 1, choose a u, 7 theta plus 3. Step 2, calculate du. Du is du d theta or 7 d theta. Do I have a 7 d theta up here? No, I only have 1 d theta. So I'm going to divide by 7, and I'm going to use the substitution. D theta is equal to 1 over 7 du. And then I have everything that I need to use. The integral that we want to calculate is equal to 1 over 7 integral of cos u du. And the rest of this I leave for you to read. Find the integral of x squared sine of x cubed dx. This integrand has both x squared and x cubed. Which one should we choose to be equal to u? And the answer is we're going to choose u is equal to x cubed. Why? Because when we then do du is du dx dx, we get 3x squared dx. And that's how we're going to cancel out the x squared. Divided by 3, we're going to be using the substitution formula. 1/3 du is equal to x squared dx. That's what we need. Now we're ready to calculate this. The integral of x squared sine of x cubed dx. We replace the x cubed by u. And we replace the x squared dx by 1/3 du. And then it's easy. Minus 1/3 cos u plus c. Replace the u by x cubed. We get the final answer. Minus 1/3 cos x cubed plus c. Find the integral of x square root of 2x plus 1 dx. Choose your u. Get your formula for du in terms of dx. Divide by 2. I'm going to be using dx as a half du. And then substitute them in. Replace 2x plus 1 by u. And replace dx by a half du. But wait a minute, there's a problem here. We've still got an x here. We can't integrate until we change all of the x terms to u terms. We need to do another substitution before we can carry on. So what do? Well, let's go back to where we started with. We started with u is equal to 2x plus 1. If we rearrange this, we can see that x is equal to a half u minus 1. So what we're going to do is we're going to take this and we're going to replace x by this. Our integral is then the integral of a half u minus 1 square root of u a half du. And that's actually quite easy because that's just u to the power 3 over 2 minus u to the power of a half. And some constants which I've moved outside. An antiderivative of u to the power 3 over 2 is 2 over 5, u to the power 5 over 2. And an antiderivative of u to the power of a half is 2 over 3, u to the power 3 over 2. Substitute x back in and we get our final answer. And I leave this for you to check. 1 over 10, 2x plus 1 to the power 5 over 2, minus 1 over 6, 2x plus 1 to the power 3 over 2, plus c. Don't forget the plus c. There's always 1 or 2 points for that in an exam. Or 1 or 2 points you could lose if you forget to write the plus c. Find the integral of sine squared x dx. To calculate this integral, we're going to need to use one of the trigonometric identities. And we're going to be using sine squared x is equal to 1 minus cos 2x over 2. So we substitute that in, and then we can do our integration and find our answer. We need to integrate 1 minus cos 2x. An antiderivative of 1 is x. An antiderivative of cos 2x is a half sine 2x. And then we get our final answer, a half x minus a quarter sine 2x plus c. Similarly, and I'm not giving all of the details here, I leave this for you to check for me. The integral of cos squared x dx, we'd use the identity that cos squared x is the same as 1 plus cos 2x over 2. Do the integration and simplify. Please check for me. A half x plus a quarter sine 2x plus c. An example I've taken from your textbook. The integral of 1 minus 2 sine squared x sine 2x dx. Well, the first thing to do is to simplify this somewhat. Remember, sine squared plus cos squared is equal to 1. So that's the first thing to do. The first bracket can be written as cos squared x minus sine squared x. But as it says in blue, cos squared minus sine squared is the same as cos 2x. And cos 2x sine 2x is the same as a half sine 4x. Then we can do a substitution, or you might just be able to see an antiderivative straight away. An antiderivative of a half sine 4x dx is minus cos 4x plus c. Is there a typo there? Well, anyway, I'll check that later. One more example before we take a break. Sometimes there's more than one choice of substitution that we can use. Sometimes each way will work. For example, evaluate the integral of 2z dz over the cubed root of z squared plus 1. Method 1, again taken from your textbook, do the substitution u is equal to z squared plus 1. So then du is 2z dz, and this simplifies to the integral of u to the power minus a third du. We know how to do that. We end up with our final answer. You can check the details. Or method 2, we could do a different substitution. Instead of u is equal to the cubed is equal to z squared plus 1, we could do u is equal to the cubed root of z squared plus 1. Now, if we do this, it's a little bit more complicated to get our second substitution formula. We need to use implicit differentiation to find that 3u squared du is equal to 2z dz. But if we do the extra work first, then we end up with an even easier integral. 3 times the integral of u du. And that's very easy, of course. And then we end up with exactly the same answer as before. And that brings me to a nice place to take an 11-minute break. We will continue the lesson at 3 o'clock. Our final topic for this week's lesson is substitution and area between curves. We've done the substitution for indefinite integrals. Now we're going to be doing the substitution method for definite integrals. I start with the theorem. Most of this is the same as the theorem that we've seen already. We need g to be differentiable, we need g prime to be continuous, and we need f to be continuous. And then in the equation at the bottom, all of the black writing is exactly the same as before. The difference I've put in blue. When we do the substitution for definite integrals, we also need to change the limits of integration. A, we need to change to g of a, and b, we need to change to g of b. So, for example, calculate the integral from -1 to 1 of 3x squared square root of x cubed plus 1 dx. And I'm going to solve this problem 2 times. First, I'm going to use the previous theorem, the theorem on the previous slide, to solve it. We start just as we did before. Step 1, we need to choose a u. Look at it in the integrand, I see there's a 3x squared there, and there's an x cubed plus 1. It makes sense to choose the x cubed plus 1. Why? Because when we differentiate it, we get the 3x squared. Step 2, we do du is du dx dx, or 3x squared dx. And we have that in our integrand. And then we need to do an extra step. Now that we're doing definite integrals, we also need to change the limits of integration. At the bottom, we started with u is equal to 1. So we started with x is equal to 1. If we put -1 into the orange formula, we get -1 cubed plus 1, -1 plus 1, or 0. And at the top, we were told the upper limit of integration is x is equal to 1. If we put 1 into the orange formula, 1 cubed plus 1, u is equal to 2. Let me repeat this green line. We need to change from x is equal to -1 and x is equal to 1 to u is equal to something. And we use the orange formula. U is equal to x cubed plus 1. For the lower limit, x is -1, so we have -1 cubed plus 1, which is 0. So our new lower limit of integration is going to be 0. And then we do the same thing for the upper limit of integration. In the orange formula, replace x by 1, we get 1 cubed plus 1. Our new upper limit of integration is going to be u is equal to 2. And then we're ready to calculate the integral. We've done our preparation. Now we're ready to integrate. And I'll try to color code this. X cubed plus 1, we replace by u. Three x squared dx, we replace by du. And then in green, we have the limits of integration. The lower limit, x equal to -1, is the same as u equal to 0. And the upper limit, x equal to 1, is the same as u equal to 2. And then we've changed our difficult integral into an easy integral. All we need to do is to calculate the integral between 0 and 2 of the square root of u du. An antiderivative of the square root of u is 2/3, u to the power 3 over 2. We need to calculate this at 2 and at 0. And I'll leave the details for you to check. Please check that I didn't make a mistake here. Please check that the answer is 4 root 2 over 3. So that was solution 1. We can also solve this problem in a different way. We could do this in 2 steps. First, we could find the corresponding indefinite integral, and then we could use that to find the definite integral that we want. So first, we're going to find an indefinite integral. So instead of -1 and 1, we're just going to cross these off and find the indefinite integral of 3x squared, square root of x squared plus 1 dx. Same substitution, u is x cubed plus 1. Same second substitution formula, du is 3x squared dx. And we find that this is 2/3 x cubed plus 1 to the power 3 over 2 plus c. That's just the theory from before the break. Now that we know the general antiderivative of our integrand, we can calculate the definite integral that we want. We put our antiderivative in here. We're going to calculate our antiderivative at same limits that we start with, -1 and 1. So put in 1 first and then put in -1. You can check the details. We get exactly the same answer as before. So let's compare the 2 methods. Solution 1, there's a little bit of extra work near the start in this green line, but then the end is quite easy. Or if we use method 2, we don't do the extra work at the start. There's no extra green bit here. But when we get to the end, it's a little bit more complicated at the end, a little bit of extra work at the end. You can choose whichever method you prefer. In the following examples, I'm going to be using method 1. Calculate the integral from pi over 4 to pi over 2 of cotan theta cosec squared theta d theta. Okay, now there's 2 functions here. There's cotan theta and there's cosec theta. We should choose one of these to be u. And it's not obvious from looking at it which one to choose. So what we do is we choose one of them and we try it. If it doesn't work, we'll go back to the beginning, we'll choose the other one. For this example, the one that works is to choose u is equal to cotan theta. Why does it work? Because when you differentiate cotan, you get minus cosec squared. And that's how we cancel off the cosec squared. Take the minus sign of both sides. Minus du is cosec squared of theta d theta, which is what I have in the integral. Because we're doing definite integrals, we do need to do an extra little bit of work here. We need to change the limits of integration. Instead of theta is pi over 4 and theta is pi over 2, we need to change these into u. Looking at the bottom one first of all, theta equal to pi over 4, if u is cos theta, is the same as u is cotan pi over 4, or 1. And for the upper limit of integration, instead of theta is pi over 2, u is cotan pi over 2, which is 0. The new upper limit is going to be 0. We've done all the preparation. Now we can do the integral. So what are we doing? So cotan theta becomes just u. cosec squared theta to theta becomes minus du. Lower limit theta is equal to pi over 4 becomes u is equal to 1. And upper limit pi theta is pi over 2 becomes u is equal to 0. So all we need to do is to calculate the easy integral minus the integral from 1 to 0 u du. And I'll leave it for you to check that that is equal to a half. Now, when I'm doing this method, I like to write x equal to and u equal to in my upper limit and lower limit of integration. You don't have to do that if you don't want to. If you understand which is which, then if you want to, you can just write 0, and if you write 1. I prefer to write x equal to or u equal to if I think there's a chance that I might be confused. I leave that completely to you to decide. One more example from the textbook. The integral from 0 to pi over 2 of 2 sine x cos x over 1 plus sine squared x all cubed dx. We need to do a substitution. And the substitution we do is we let u be equal to 1 plus sine squared x. So we're just going to be left with u cubed on the bottom. Great. If we do this substitution, then du is 2 sine x cos x dx. And that's exactly what we have. That's just the same as du. And then one more thing we need to do, we need to change the limits of integration. For the lower limit, x equal to 0 becomes u equal to 1. Why? Well, if we put 0 in here, 1 plus sine squared 0, side of 0 is 0, so it's just 1 plus 0, 1. And x equal to pi over 2, put pi over 2 into 1 plus sine squared x, we get 1 plus sine squared pi over 2. That's 1 plus 1 squared, or 1 plus 1, or 2. But our new upper limit is going to be 2. So the new lower limit is 1, and the new upper limit is 2. If you understand what you're doing, you don't have to write x equal to or u equal to here. You can just write the numbers 1 and 2. If you think if you're doubting whether or not you'll get confused, then you could do what I do, and you could write u equal to 1, u equal to 2 here. So then we have our easy integral from 1 to 2 of 1 over u cubed du. I'm going to skip the details. You can check that that's 3 over 8. So that is the substitution method for definite integrals. One more idea for this week's lesson. I also want to talk about the area between curves. And this is going back to the idea of total area that I talked about earlier. Looking at this picture, I have some area which is between the blue curve and the red curve for x between a and b. And if we say all of this area is positive area, what is the area which is shaded in blue just here? We have a definition. I'll come back to the details first. Look at the formula at the bottom. The area shaded in between the blue curve and the red curve is just the integral from a to b, f of x minus g of x dx. F of x is the bigger function, g of x is the smaller function. Now let's go through the details. If f is continuous, if g is continuous, so not weird functions, nice continuous functions, we need f to be bigger than g on the area that we are integrating. We don't care what happens over to the left. We don't care what happens all the way over to the right. We only care what happens between a and b. And between a and b, the bigger function needs to be f, and the smaller function needs to be g. Why? Because we're doing f minus g. It needs to be big function minus small function. Then the area of the region between the curves y is equal to f of x and y is equal to g of x for x between a and b is the integral from a to b, integral of f of x minus g of x dx. Okay, so this is our formula. Let's do some examples using this formula. Find the area between y is equal to 2 minus x squared and y is equal to minus x. We want to calculate the area which is shaded light blue here. We can see that 2 minus x squared is our bigger function and minus x is our smaller function, but what are our limits of integration? To find our limits of integration, we need to look to see where do these two functions intersect. Well, they intersect when the two functions are the same. They intersect when 2 minus x squared is the same as minus x. So starting with that, and then rearranging, we can find that x is minus 1 or 2. Okay, so this number here must be minus 1, and this number just here must be 2. We need to integrate from minus 1 to 2. So this area, this blue area, is going to be the integral from minus 1 to 2, bigger function minus smaller function. 2 minus x squared minus x squared. And here's the details. I'm not going to talk about the details. You should be able to repeat this yourself. Please check that the answer is 9 over 2. Find the area bounded by y is equal to the square root of x, y is equal to x minus 2, and the x-axis for x and y both greater than or equal to 0. So we want blue area plus pink area. What are the limits of integration going to be? Well, this is 0 and this is 2, so that's the blue area taken care of. But what is this number? We need to find where the two curves intersect. So I start with square root of x is equal to x minus 2. Square both sides. X is x minus 2 squared, or x squared minus 4x plus 4. Rearrange that to 0 is equal to x minus 1, x minus 4. X must be 1 or 4. So if 2 is here, what is this number? Is this 1 or is this 4? Of course, this must be 4, right? Why can it not be x equal to 1? Well, x equal to 1 doesn't satisfy the equation that we started with. Square root of 1 is not the same as 1 minus 2. So it must be x equal to 4. Okay, so this is 4 now. We need to do blue area plus red area, or pink area. So we're integrating from 0 to 2. On the blue area, the top function is square root of x and the bottom function is 0. And then we're going to do plus integral from 2 to 4. Top function is root x, and bottom function is x minus 2. And again, I'm not doing the details here. You can fill this in for me. Please check that this is equal to 10 over 3. So that was integration with respect to x, but we could also do integration with respect to y. Instead of a picture like this, let's suppose we have a picture like this. Instead of a top function and a bottom function, we have a left function and a right function. Then the area of this region is going to be the integral between c and d of, now the bigger function means the function on the right, and the smaller function means the function on the left. So it's going to be f of y minus g of y dy. An abbreviation I'm going to be using a lot, WRT, I mean with respect to. Find the area bounded by y is equal to the square root of x, y is equal to x minus 2 in the x-axis, for x greater than or equal to 0 and y greater than 0. We did that before, but there's an extra statement here. By integrating with respect to y. Now we're going to be integrating between two different values of y. The smallest possible value of y here is y is 0, and the biggest possible value of y in this blue area is y is 2. So we're going to be integrating between y is 0 and y is 2. So there we are, integral from 0 to 2. And then it's going to be function on the right minus function on the left. Well, on the right, we had y is equal to x minus 2. That's the same as x is equal to y plus 2. And the red function was y is equal to the square root of x, but that's the same as x is equal to y squared. So it's going to be y plus 2 minus y squared. And if you finish this calculation for me, please check that the answer is 10 over 3, which is the same thing we found earlier. So it's probably correct. Here's another one. Find the area of the region shown below. This is exercise 33 on page 322 of your textbook. So, what are our limits of integration? The smallest y here, y is 0. And the biggest value of y at the top is y is 1. And then it's going to be function on the right minus function on the left. The function on the right is 12y squared minus 12y cubed. And the function on the left is 2y squared minus 2y. And if you check all the details for me, the answer is hopefully this is correct. Please check that the answer is 4 over 3. And that's all I have for this week's lesson. That is the end of chapter 5. Next week, we're going to talk about all of chapter 6. We'll do volumes using cross sections, volumes using cylindrical shells, arc length, and areas of surfaces of revolution. Are there any questions? So this one minus the integral from 1 to 0 of u is exactly the same as the integral from 0 to 1 u du. So yeah, you could do that. That's one extra step just here. Then we get plus 1 to 0. These two swap place, and it's plus, and then we end up with exactly the same answer. It doesn't matter. You end up with the same answer.